This is the second part for nuclear physics. In this, we will see what is being spontaneous and what is the meaning of random nature of radioactive decay. So first, we will talk about randomness of radioactive decay. What is the meaning of being random? So randomness basically deals with the fact that everything will be unpredictable. And what things or what factors are actually going to be unpredictable? What is the factor that he says is going to be unpredictable? In a sample, for example, we have a sample of uranium, and there are a number of atoms of uranium in the sample. Which atom is going to decay? We don't know. This is unpredictability. And in which direction will they release radiation? Alpha, beta, gamma, whatever that is, it is not known. Again, this is unpredictability. And each nucleus is or has the same chance. The second point, any one of them could decay. We can't predict which one is going to decay. So this is randomness of the nuclear decay. And we observe this in the radiation or the level of GM tube readings. That if, for example, we have a sample at the center, we have GM tube in 4 locations, for example. Let's say this is GM tube. This is also GM tube. This is also GM tube. This is also GM tube. We have it in 4 locations. The radiation received by these GM tubes, even though they are at the same distance, they will give out different readings. For example, this could be giving 4,000 counts per minute. This could be given 3,800. This could be giving 390.78. This could be given 4150 reading. So although they have the same distance, but the radiation received by them is different. This also adds to the randomness of radioactive decay. And this is observed on graph as well, which is according to the first point of the syllabus, that there is fluctuation in the count rate. You see, in O levels or at low levels, we believe that this is what the decay curve actually looks like. This is actually averaged out. This is smoothed out for mathematical calculations, but in real life, the graph is actually sometimes an overestimation, or you can say it gives us a value higher than the average, or sometimes it's lower than the average. So sometimes the decay is faster, sometimes the decay is slower. Again, this also adds to the unpredictable nature of radioactive decay and the randomness of the radioactive decay process. So you will see this as the first point in the syllabus, and in the second point, he also enforces randomness, which is linked with the first point. What is the meaning of being spontaneous? You can pause the video and see for yourself and read this for yourself, but let me give you a small summary of this. Spontaneous would mean that this reaction is not affected or is not controlled by external factors. For example, if you add any acid or any base or any chemical on the radioactive sample, the decay rate will not be affected. For example, you add pressure to the sample, it will not affect the rate of radiation. For example, you heat it up to a very high temperature, it will still not affect the rate of radiation. So basically, any chemical process or any process related to chemistry that you've done is changing pressure due to Le-Chatelier's principle, or providing heat, which increases the kinetic energy, and in a chemical reaction, it speeds up the reaction as well. And for ace and base, of course, they provide free radical hydrogen and hydroxide ions, which actually causes unprecedented rate of reactions, but nothing like that happens in this situation. That is a part of chemistry, which this radiation or this part of physics, we see that it is not helping. It's not changing anything or the rate of reaction. This is the true graph of radiation, or the actual radiation coming out from a radioactive sample. We will solve a question regarding this as well. So we're done with the first 2 points. Let's move to the point number 3, which is that students must recall this equation, A equals to lambda n. Let's look at this equation. What is this? So A starts with A being proportional to n. What is A? A is called activity, and n is number of atoms. Be advised, what number of atoms? Are these the number of atoms that are supposed to decay? Are these before decay? Are these after decay? But what number of atoms? So number of atoms still undecayed, still present in the sample, which have not undergone the process of radioactive decay. So if you have a high number of atoms still left out, the activity will be high. This is what this equation tells us, that if remaining atoms are high in concentration, which have not decayed yet, then the activity will be high as well, which is what we see in the decay graph as well. That if we have, let's say, 100% of the elements or of the atoms that are going to decay, they decay very quickly at the very beginning, but then the rate of decay slightly gradually becomes weaker or becomes slower. So the gradient The rate of decay is very fast at the beginning. It gradually slows down, eventually becomes zero after a very long time, of course. So if the number of atoms remaining are low, the activity will also be low. And activity, to a simple common man understanding, what would that mean? It means how many atoms, or you can say atoms or radiation released per unit time, right? And the n represents number of atoms. Now, to convert this into an equality, we need to introduce a constant, which is A equals to negative lambda n. We go back to the syllabus and we realize that there is no negative sign in the syllabus. Sometimes you will see a negative sign, sometimes you will see a positive sign, sometimes without the sign. Negative only means that this is a slowing down process. It is always releasing the number of atoms, and it's always going to be a negative gradient curve, which is evident from this equation, right? Okay, so let's deal with as a positive formula as A equals to lambda n. What is the meaning of lambda? Lambda is referred to as the decay constant. What is the meaning of decay constant? And the unit is very interesting. It is 1 per second. It is 1 per minute. It is 1 per hour. It could be 1 per week, per year, per so on and so forth. Could be with any time. But what does that mean? It actually tells you about the probability. Probability or chance of decay. For example, if the lambda has a value of 200 per second, that means that there is a chance that from this sample of God knows how many atoms, 200 atoms will decay in 1 second, right? So decay constant only tells us about the probability that how many atoms are going to decay in 1 second. So from this, we also get to another formula with this in terms of rate of change, that activity is equal to change divided by change in time, which is very plausible because we understand that decay constant has a unit of 1 divided by time. So when you replace that over here, n comes in the numerator and the lambda actually translates into 1 by t. So this formula is also acceptable because this formula actually looks at the gradient itself, right? Okay, because on this axis we have time and in this axis we have number of atoms. So y-axis divided by x-axis gives us number of atoms divided by time, which also becomes activity, as it devised earlier, that this is actually, this negative sign actually copes with the gradient of this graph. Anyways, moving on to this formula, okay? And the common unit of activity in your syllabus is becquerel. So what is the meaning of becquerel? Becquerel means that one atom has decayed in 1 second. This makes it very convenient for us, although the numbers are generally high with this unit, but this makes it convenient for us to visualize at least that how many atoms are decaying at the certain instant, right? For example, let's say that lambda for a certain radiation, certain component is 0.2, right? It's 0.2 second minus 1, or let's say it is per minute, okay? And the current number of atoms in the sample are 1000. So if you find the activity, that would be 0.2 multiplied by 1000, that would come out as 200 becquerel. What does that mean? It means that in 1 minute, 200 atoms would have decayed and would have left the sample after radiation. Now, how many number of atoms are left after that 1 minute has passed? You see, you started with 1000 atoms, and after 1 minute has passed, you are left with only 800 because 200 have decayed out. They have left the sample. Okay, so what will be the activity now? So let's recalculate the activity. The decay constant remains a constant, as it is a constant and it does not change. Multiplied by right now, since the formula was n represents the number of atoms undecayed, left behind, who have not decayed, we are left with 800 atoms right now, right? So activity comes out as 160 becquerels, which not becquerel, but you can say that this is per minute, so it has to be in 1 second. If we divide this with 60 and divide this with 60, then we can use the becquerel unit. You can ignore this for now, okay? Let's, for the sake of understanding, consider this at face value, that 160 atoms have decayed in 1 minute. You see, the relationship that we started with was A proportional to N. Now, if the number of atoms have reduced because it is a decaying sample, the activity reduces as well. You see, the activity previously was 200. Now it is 160. Previously, in 1 minute, 200 atoms had a chance to get released. Now, after 1 minute has passed, only 160 atoms have a chance to get released after the nuclear decay process. So this equation is important in terms of visualization, at least. Okay. All right. So we understand this formula as well. We are going to look at this half-life concept after a while, because first we need to understand this equation. Now, this is an exponential decay equation, which we have done in capacitors topic as well. What is the meaning of this equation? This equation is actually the mathematical representation of this graph. This is an exponential decay curve. Now, he tells you that this x is equal to x naught e raised to power minus lambda t. You can choose x to be anything. What is that anything? So it could represent activity, which is A in our formulas, number of undecayed atoms, which is N, and the received count rate, or the CPM received from the GM tube, right? So this equation will convert into involved as, if we replace activity in this formula, then this equation becomes this one. If we replace the number of atoms, then it becomes this equation. And lambda, of course, is still the decay constant, right? And if we want to involve the count rate, then that will be C is equal to C naught e raised to power minus lambda t. Of course, what is the utility of this equation? I will put this time t of my choice, picking it from the graph. At what time do I want this to happen? And from the very starting point, which is this point, which is your original atoms A naught, N naught, or the starting count CPM, the very beginning of the reaction, you put those values over here, and after a certain time, when you put that time t over here, it will give you that current value of N. Let's say you put in the value 50. So it will tell you the current value of N, A, or CPM. That after this time has passed, what is the value of current level of activity, so on and so forth. Okay. All right. So this is what he wants you to understand. Now we understand point number 6 as well. Now we move towards half-life and this formula, that how this formula is actually going to be made. Okay, so half-life we understand we define by the fact that it is the time taken for the radioactive sample to decay to half of its original value. How much time will it take to reduce its activity by half? So for example, if it is releasing, let's say, 1,000 atoms at certain time in its life, after how long will its activity fall to 500? Most definitely, this is what we're looking at. We know that it is decaying, right? So at what time does it only have 500 atoms, or its activity is only 500 radiations or becquerels left? So this time is what is called half-life. Now we're going to do its proof in terms of the formula that is mentioned in the syllabus. Let's go on with this one. So let's say that we start with the number of atoms. So N is equal to N naught E minus E raised to power negative lambda T. Now, since we're looking for 50% of the atoms, which means that after time t, after a certain time t, these number of atoms will be half of the original value. So if I write this down, N as 0.5 N naught compared to the original equals to N naught, then there is no problem in this assumption, because I want to find the half-life. I want to see when it becomes half. If this is N naught, then this is N naught divided by 2, or I can write this down as 0.5 N naught. This is what I've written down over here. Now, consequently, N naught gets cancelled out from both sides, and I'm left with this 0.5. So 0.5 is equal to e raised to power minus negative lambda t. Now you have to take natural log on both sides, right? So if you take natural log on this side and natural log on this side, you are left with this equation. ln of 1 over 2, now I've converted this into 1 over 2, equals to ln of e raised to power negative lambda t. We know from logarithmic rules that the power can be taken outside, and we know that ln of e is equal to 1. You can do this on the calculator and see ln of e will be equal to 0. This e is an exponent which has a power of 2.71, which has a value of 2.71. So what are we left with? We are left with the ln of 1 over 2 equals to negative lambda t ln of e. This is going to become 1. We are left with the ln of 1 over 2 equals to negative lambda t. Now what you can do is, you can calculate this ln 1 over 2, and you will find out that the answer is going to be negative 0.693 equals to negative lambda t. Now, since we were dealing with half-life, or we wanted to calculate the half number of atoms, I'm going to change the representation of this t to t1 over 2, because now this time or as this time has passed by, I will be looking at half the number of atoms, right? So I'm going to change the representation of this letter, plus the negative sign gets cancelled out from both sides. So what are we left with? We are left with a 0.693 divided by lambda equals to T1/2, or half-life. This is the formula that is written in your syllabus, which is represented over here in point number 5. We've discussed what is half-life. We've also discussed how this formula is going to be used. Okay, I've written down it in terms of T being the subject of the formula, 0.693 divided by lambda. But we can see by performing simple algebra, we can change their positions. T can be brought here and lambda can be brought there to make it look like this one. What is the importance of this equation? This is a very important equation because this helps us to identify the half-life. If I know the decay constant given in the question, then I can very well predict the half-life. And if I know the half-life, I can very well calculate it with this method, that how many number of atoms will be left after a certain time. Okay. All right, let's move to a simple question. This is also a part of the syllabus, which is not mentioned here, but I will discuss it. That is why I'm doing this question. He says that a radiation detector close to reactive source, the reactive does not surround the source, radiation in all directions, good. And as a result, the activity of the source and the measured count rate are different. Now, what is this problem? He says that the actual activity of the sample, how highly active this is, cannot be measured accurately or is not measured accurately. Why? Because our detector, the GM tube, is only in one location, right? It can only expect the radiation coming directly at it. What about the rest of the radiation? How will we capture that one? So it is not possible. We can't do that. What is the actual activity of the radioactive sample? So this is called A, the actual activity, and this is called R, the measured activity. Now he's going to ask you the reasons for that. What could be the reason that these are not similar and why they are different? So it could be possible that there is some emission from the daughter particle. What is a daughter particle? What the parent is going to form after the decay. It's possible that the daughter particle is also radioactive. So there are some radiation coming from that. So the true nature, the true radiation that we wanted to measure is now polluted with a value coming from a parent and some value coming from the daughter. So it was going to mess with our results. Then, of course, some radiation absorbed inside the sample. Some radiation absorbed inside the sample in its own as self-absorption. And some radiation is absorbed in air, right? And it's possible that the window of GM tube, which is made out of glass, window of GM tube also absorbs some radiation. So all in all, the true nature of the radiation is not being received by us, is not received to us. Why? Because we are left with some absorption in the respective mediums, in the respective transfer or during transfer. Okay. All right, so these are a few points that you can remember, that why actual activity is not going to be equal to the measured activity. What you can measure with the GM tube is far less than the actual activity, which is why radioactive nature, radioactive decay is already dangerous in its own. Because if you are measuring that the value of, let's say, radiation is 15,000 or 20,000 becquerel, then the true value is going to be much, much greater than this because you weren't able to measure it in the first place. Okay, this is just an estimation, which is why it should always be avoided, and it is a very dangerous process. Okay, so the variation of time t of a radioactive sample, you can see that there is a fluctuation in this reading, and this is what the actual reading of a radiation or radioactive source looks like. It's different from O levels. So it tells you that what tells us from the graph that the radioactive decay is random in nature. So we can say that the count rate is not smooth. Or you can say that there are fluctuations in the reading. Fluctuations in the curve are actually representative of the randomness. This is what we started with. This is the main discussion point of randomness and spontaneous. He says determine the half-life, and the question is for 4 marks, which means it requires a lot of working from your side. Now let's try to make it simple. So we know that background radiation does not participate in the process of getting halved. Right? That is what we've done in O levels. So first, let's figure out what is the half-life. You see, the standard value beyond which the graph is unable to fall down, it means this is our background radiation. Why? Because our sample is still decaying. It will never stop decaying. It will decay. But why is this not being detected, but the background radiation is? Because right now, background radiation is stronger than the actual radiation coming from the source. So this poses a problem. We don't want to include background radiation in our calculation because it never decays. Its value will never change. So this whole graph is actually misrepresented by a value of background radiation. Now, what is that value? So according to my calculations, this is going to be 10. So my background radiation comes out as 10 because it's not falling down below that value. Okay. Now, when I pick a value from this point, let's say I pick up a value of 170 as the peak. Now, notice that this is also just an average guess. You could have selected 171, you could have selected 175. It does not matter. Okay. There will always be a range of answers. Now, notice that is this 170 purely coming from a radioactive source? No, it is polluted by background radiation as well. So what I'm going to do, how will I compensate for this? I know that 170 is not purely from my source. So I will subtract background radiation to compensate for the effect, because background radiation does not get halved. It is not going to get participated. It's not participating in the halving process. So I'm left with 160. This is my true value of the source. Now I will divide this by 2 and get a value of 80. My source will emit 80 radiations, but combined with the background radiation, because I have no way of avoiding this, my actual GM tube reading is supposed to be 90. This 90 will be read from the graph. Second, I have to calculate the half-life at least twice to eliminate any errors of time that I'm going to calculate, because at the end we're going to take the average. Now, then I'm going to take 80 back again, because 80 was the original source radiation. Divide this by 2 and I get 40. Now, I know that 40 will not be read by the GM tube. The GM tube will be reading an overcompensation reading or overcompensated reading with the background radiation. So that will be 50. Now, these are the values that we are going to check from the graph. This will be checked from the graph, because graph already shows an addition of background radiation. It's already polluted. Okay. So let's go back to the value of 90. So I get at somewhere along the center point, I get to this point, and then I see that this is an average value of 1.5. Okay, right. The second value was around 50. Now 50 is around this point. So we get to this point and we come down at 3, which means that our average half-life is coming as 1.5 and then 3, which means that in both durations, it is actually around 1.5 hours. Right? So if I take this, this is 1.5. If I take this, this is 3.0 hours. This is 1.5 hours. And if I divide this by 2, I know I have gone for at least 2 half-lives, because we started with 160, we got 80, and then we halved again to get 40. So these are 2 half-lives again. This gives me an answer of 1.5 hours, which means that my first half-life that I found and the second half-life are exactly the same. They could have small differences, but no need to worry about that. So my half-life is going to be 1.5 hours. And please notice that since this question is for 4 marks, please do not forget to draw these lines on the graph so the examiner knows how you have done the question. You need to show the examiner how you have done the question. Please don't forget to draw lines, or to at least label the graph so that the examiner knows that how you did it. Are you going to copy it? Have you copied it from someone, or are you doing it on your own? This is important. So you have to tell the examiner that you were capable of doing this. Next question, he says, what will be the effect of increasing the temperature, so and so? You can pause the video, read the question. I'm going to get straight to the answer. He says, state any difference, if in any, in the half-life. There will be no change in the half-life. No change in half-life. Why? Because radioactive decay is a spontaneous process. So it is not affected by temperature. It doesn't do anything. What is going to be different about the measured count rate for any specific time? Now, we cannot predict count rate. Count rate cannot be predicted. Why? Because it produces fluctuations in the graph. It produces fluctuations in graph. And since it is unpredictable, we will say that this is a random process. Now, since this is a random process, or any random process, can you ever give an answer with 100% surety that this is the count rate? Apart from and including the effect of different radiation from different sides, including the effect that all the radiation is not being received by the GM tube radiation, and the effect of randomness as well. So this unpredictability is calling me, or you can say is limiting me to give a confirmed answer for this question, and I'll have to leave it at random process, fluctuation, count rate, and that this is unpredictable. We cannot say whether it's going to increase or it's going to decrease. Not because there is a problem with the question, but because in reality, in actuality, we can't do this. We can't do that. Okay. All right.